Hi, everybody, and welcome back to the second part of the second part of the first lecture on confidentiality, where we're going to talk about practical secret key encryption schemes. So let's recall, why are we here? What do we do? So in the first video, we've seen that if you want perfect secrecy, if you want a scheme which has unconditional secrecy, you can use one-time pad. That's a great encryption scheme. It has unconditional security. Unfortunately, it's also very impractical, since the key has to be as long as the message, and the key can only be used once. In practical encryption schemes, you want the key to be much, much shorter than the message, and you want to be able to reuse the key multiple times. If you want to encrypt, if you want to do secure communication between your laptop and some website that is sitting over somewhere over the internet, it's simply not practical enough to think that you need to have a key which is as long as the amount of communication that you're going to exchange. So you want the key to be short, and we're going to see this later, but typically by short we mean like 100, 200 bits. So relatively short key, and this key can be used to encrypt very large amount of data, for instance, megabytes or gigabytes of data. So the syntax of the scheme didn't change. You still have an encryption algorithm, a decryption algorithm, a key generation algorithm that produces a key. You just want to be able to use the key over and over again. So the main issue, when we talk about practical encryption scheme, the first thing that we need to ask is how long should the key be? And as I already told you, the key in practice is going to be something like 100 to 100 bits. How do we decide how long the key should be? There are many ways. I mean, essentially, you choose the key to be as long, so long that there are no known attacks which can break the system. So the key needs to be long enough that regardless, that the adversary can't break it using reasonable resources. So the first attack, the most general attack that we can see on any practical encryption scheme is what is known as exhaustive search. As the slide says here, every practical encryption scheme can be broken given enough time using exhaustive search. And then the trick will be, how do we set the parameters right in such a way that this attack is essentially impossible in practice, or where the attack would take essentially forever. So I'm going to go to the board and do this. Right. So we have an encryption scheme where, let's recall, you have a message, you can encrypt it using some key and get a ciphertext. So for exhaustive search, so this is, remind this, so exhaustive search. We're going to make an assumption. The assumption is that the adversary knows, one or more pair of ciphertext and messages. So let's say that for simplicity here, let's just say that the adversary knows one such a pair. The adversary knows one message and one ciphertext, such that when you encrypt this message with the key, you get this ciphertext. How did the adversary get these? There can be many explanations for this, but if you think, for instance, about web traffic, the ciphertext, the adversary gets the ciphertext because the ciphertext is what is sent on the public channel. So it's not very hard for the adversary to get hold of the ciphertext. This is just part of our model. But why does the adversary knows the message which corresponds to that ciphertext? This might sound a bit tricky, because usually, I mean, the message is what we're trying to protect. The message should be secret. But again, think about a communication between your computer and some website. You kind of know a lot of information about, the adversary will know a lot of information about the encrypted traffic. Maybe the adversary doesn't know if this is like your Gmail account. The adversary doesn't know the content of your emails, but the adversary knows everything else about the structure of Gmail website, because the adversary also can access the same website. So the adversary knows that the website starts, that the HTTP request will start with an HTTP tag, and then there's going to be some headers which are always the same, and then there's going to be some information, some HTML tags which are always the same. So there's a lot of information which, even if it's encrypted, the adversary already knows what it is. If you've seen the movies about World War II with Alan Turing, you know that in World War II, the British were able to break the Nazi encryption mechanisms because they knew that the first thing that the Germans would do in the morning was to transmit the weather forecast, and the British could also see the weather forecast, and therefore they knew what was the first message of the day. And the first message of the day was something along the line of, hello, today is the date, blah, 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 and the weather forecast is this and this and that. And if you know, I mean, if you can predict these things, then you will know what it is. So the adversary knows one pair and ciphertext message. So a little bit more of notation that I need here is that the key, like it was in the previous slide, the length of the key is T bits. And the length of this message is, let's find it over there. The length of the key is T, and the length of the message is U bits. That's gonna help. So now I'm gonna write down how exhaustive search works. So the first step of exhaustive search is simply to initialize a list to be the empty set. So far, so good. Then we're gonna do a for. So we're gonna do for each a for loop where for each possible key from the old 0 string to the old 1 string, exhaustive search will do for every possible key. We'll compute some message. Let's call this to A. It's going to compute some message M prime, which is obtained by decrypting the ciphertext here using this key K. And then it should be, let's say that if M prime is equal to M, we add the key K to the list N. And then the last step of the algorithm is simply to output the list N. So what does the algorithm do? Simply initializes a list, then tries to decrypt the ciphertext using every possible key which is in the key space, gets some message which might or might not be the right message, and if it's the right message, the algorithm says, okay, this key, let's pretend it, let's assume that this key is a good key, let's output it. If it's not, we exclude this key and we remove it. So now we need to ask two questions about this algorithm. The first one is, does it output the right key? And the second one is does it output any other key? So first of all, does it output the real key? So the real key is this one, the one which was actually used to encrypt this message into the ciphertext. So the real key is being output. Why? Because the encryption scheme is correct. So when the algorithm loops through the keys and gets to this value, the decryption would be correct. So the correct key will go into the list. So far, so good. And now, will any other key be into this list? Will you get false positive? Will you get keys which are wrong keys into the list? The list is, of course, useless if the algorithm outputs every possible key. So here, let's make an assumption, a reasonable assumption, that if you decrypt a ciphertext using the wrong key, the output will be uniformly random. This is not true in one-time pad, because one-time pad did the XOR between the key and the ciphertext, so the output wasn't completely random. But you will see later, we will see later other examples of one-time pad is not an encryption scheme that you can break using exhaustive search, so it doesn't matter. When we're going to look at later, we're going to look at practical encryption schemes, practical symmetric encryption schemes, which can be modeled by this property. If you decrypt a ciphertext using the wrong key, you'll get something, a message which is completely random. Then you can ask, what is the probability that how many wrong keys will get into the list? Now, so I guess I can write it here. So here I already defined my notation, so I'm in good shape. I'm gonna take away a little bit of this. So the probability that a wrong key, the probability that the cipher that's decrypted with the wrong key will produce the right message, if the decryption produces a random message, is going to be 2 to the minus u. That is simply the probability of hitting this particular message when you sample a uniformly random message. And how many wrong keys are there? Well, there are 2 to the t keys all in all, minus 1, which is the right one. So all in all, you get 2 to the t minus 1. So now if I have that u is larger than t, then this number is less than 1. And then you expect to see inside the list only the right key and nothing else. So let's go back to the slides. So what did we learn about exhaustive search is that you can look at the proof back again, is that given any practical encryption scheme, any scheme in which the key is shorter than the message, in which you encrypt more plain text material than the length of the key, then it's always possible to find the key which was used, given a ciphertext message pair, it's always possible to find the key which was used to encrypt this. And if you have the key, then you can break everything else which was encrypted under this key naturally. However, this attack is very impractical. Why? Because the for loop, which is the main part of the attack, has to run through every possible key. So if the length of the key is 100 to 100 bits, then it would take forever. If you have a loop that does 2 to the 100 iteration, essentially, regardless of what the content of the loop says, I mean, the time it will take to do this is essentially forever. At the beginning of 2018, and now it might be probably more, if you took the entire Bitcoin network, which is a huge amount of computing power, they were performing around 2 to the 64 cryptographic operation per second. This is a huge number. This is a number which was unthinkable of 10 years ago. The entire Bitcoin network does 2 to the 64 did 2 to the 64 cryptographic operation per second in 2018. Now it's probably, I don't know, 70 or something like that. If the key is, let's say now that the key is 100, let's choose the key to be 128 bits. Then how long does it take the Bitcoin network to go through a loop of 2 to the 128 possibilities? Well, it takes 2 to the 64 seconds. So how much time is 2 to the 64 seconds? The age of the universe is estimated to be around 2 to the 58 seconds. So that means that it's a really, really, really long amount of time. So computational security means that it is theoretically feasible to break a system given enough time, but in practice it's impossible if you set the parameters well enough. Okay. Something else which is very important when you talk about practical systems is that you need a nonce to do the encryption. You need some randomness to do encryption. So why is this needed? This is needed because you're encrypting the same, if you're encrypting the multiple messages using the same key, you will be encrypting over and over again using the same key. And what is the problem with this? The problem with this is that if you happen to encrypt the same message twice using the same key, you will get the same ciphertext. So an adversary that looks at the ciphertext that are traveling on the channel, if it sees the same ciphertext twice, they will be able to see that, oh, this must have been the encryption of the same message. This might seem like not a lot of information. I mean, you only know that these two ciphertexts contain the same message, but you don't know what the message is. And when you think of that, you should always think about the penguin. So in this slide, you can see this very nice penguin taken from Wikipedia, where you can see on the left a picture of the penguin, of the Linux penguin, and on the right, an encryption of this, where every block, so every block of pixel, has been encrypted using the same key. And you can see that everything which is white is being mapped into something which is randomish, but it's always the same. So the entire white area is encrypted to the same random block. And similarly, the black area, every block in the black area is encrypted to the same thing. So even though you don't know what the, when you see the encryption here, you don't know what the original color was behind this, still a lot of information about the original image is preserved. So when encrypt using any practical encryption scheme, so if you use, when you use practical encryption scheme, computational encryption schemes, you need to use some nonce, some randomness into the process. If we talk about security, and I mean, so far I didn't talk about security, I talked about insecurity. So we define two kinds of insecurity. one way of breaking a practical encryption scheme is exhaustive search. The other way is this repeated encryption of the same message, which allows you to discover structure of the message. Another way of now, instead of defining insecurity, I'm going to try to define what is security. So there is a gap between insecurity and security. Insecurity is what we know how to break. Security is what we know that it's not breakable. And then sometimes there is something in between where you're not sure. So before we discuss some of the attacks that we know you can run on a scheme, these attacks means that you must take countermeasures against these. Now we're going to talk about how do you define what security means. So defining security for an encryption scheme is typically done in cryptography using a game. So this, even though it's pirates and boxes and arrows, this is actually is a precise mathematical definition. So the mathematical definition says that there is an adversary, which is just an algorithm, a piece of code, and this algorithm is interacting with some box. The algorithm doesn't know, the adversary doesn't know which box is interacting with. This is like a black box that the adversary is able to play with. The adversary doesn't know which box he's playing with, and he has to guess. We say that the system is secure if the adversary cannot guess which of the two boxes he's playing with. So let's see what the two boxes do. On the left, you have the real box. What the real box does is that samples a key, like the encryption scheme would do, picks some nonce that is going to be used in the encryption scheme, and then the adversary gets to choose a message, and the box returns an encryption of that message using that nonce. Let's talk a little bit about this. Why is the adversary allowed to choose the message? Why do we want security against an adversary that already knows what the message is? I mean, security means that the adversary cannot learn what's inside the ciphertext. Why is the adversary choosing the message? This looks weird. The reason why we do this is because we are cryptographers, we are pessimistic, we are paranoid, so we want security even in the worst possible case. If I define security to hold even against an adversary that already knows what the message is, then security will also hold against any other adversary that doesn't know what the message is or only has partial information about what the message is. As we were discussing before when we were talking about the exhaustive search attack, the adversary might already know a lot of information about the message, maybe because there is some structure in the message, it's an HTTP request, the adversary knows what the date it is today or things like that. So if we ask security against an adversary that knows, that even chose the message, then we automatically also get security against adversaries who don't have all that information. Great. So the adversary has chosen this message, and now the box has picked this nonce. Nonce stands for number used once, and returns an encryption under the key of this message. Great. The adversary can do this multiple times. So now let's look at the right side. On the right side, there is this other box. What does this box do? This box also picks a random key, also receives a message from the adversary, also picks a fresh random nonce, but then instead of encrypting the message which was chosen by the adversary, it chooses a uniformly random message which has the same length as the message chosen by the adversary, and then encrypts these and returns these to the adversary. Now the job of the adversary is to distinguish whether is being returned an encryption of the message he chose or an encryption of a completely random bit string. So here the intuition is that if the adversary can't distinguish between an encryption of the message he chose and encryption of random garbage, then it must mean that this encryption scheme is very, very good. It hides all information about the message. The adversary can't even tell whether this is an encryption of something the adversary knew or encryption of some random garbage. This is the best that we can hope to achieve. Why is the box choosing a message which is of the same length of the, a random message which is of the same length of the message chosen by the adversary? This is because, unfortunately, encryption can never hide the length of the message. A famous cryptographer once said that a good mask can hide your face, but it cannot hide your height. If I take a mask, I can, maybe my face is hidden, but I can't make myself taller or shorter. So in fact, I could make myself a little bit taller, right? I mean, I could put maybe some shoes which have some filling, but I can't really make myself shorter. And this is really the problem with hiding the encryption the length of a message. So if you want to hide the length of a message you're encrypting, you might be tempted to add some extra bits to the message, such that the message gets of a uniform length. Maybe all the encryption are always of the same length, so you don't know what the length is. But this maximum length you've chosen would disclose an upper bound on the length of the message, right? So this is the state of affairs. But again, so the definition of security is the following. You have an adversary who plays with this box. Either the box encrypts the message chosen by the adversary, or the box encrypts messages which are uniformly random, and the adversary cannot tell the difference. And if this is the case, then we call the encryption scheme secure. Usually we call it secure against chosen plaintext attack. Let's see some examples. Now we talked a lot about definition, security, and security. Let's see about some examples of how we actually do encryption in practice. So the first example of practical encryption schemes that we encounter is stream ciphers. Stream ciphers are called stream ciphers because they are good for encrypting, surprisingly enough, streams of data. A stream cipher will take a short key, typically 128 bits or something like that, together with a nonce, and will extract some output here, some long output here. You can now take this long output, this long pad, and XOR it with the message in a way very similar to what we did with one-time pad, and get a ciphertext. The encryption works as you would imagine. You, from the key and the nonce, you regenerate this pad, and then you XOR it to the ciphertext, and you get the message. But the main difference between this scheme and one-time pad is that in one-time pad, the key was as long as the message, whereas here the key is much, much, much shorter. So this key here could be 100 bits, whereas the message was 1 gigabyte. So naturally, since this O is much, much, much larger than K, this O cannot be uniformly random. If the key is 100 bits, there are only 2 to the 100 possible outcomes here. And if this outcome here was 1,000 bits, there would be 2 to the 1,000 possible strings of that length, and it's just not possible for the stream cipher to produce all of them. The stream cipher will only produce a very small subset of these. But hopefully, the stream cipher works in a random-looking way, so that the output that is produced by the stream cipher is indistinguishable from a real random string, at least to a computational bounded adversary, and therefore the encryption scheme is secure. So historically, stream ciphers have had a bad reputation because most stream ciphers were broken. And the reason for this is that there is nothing wrong with the general design pattern of stream ciphers. The thing is that most stream ciphers have been designed in the past to be very, very, very fast to be implemented in hardware, and therefore were not very complex objects, which could then be broken by cryptanalysis. So we're not going to look at any example of stream cipher, because in fact, what we're going to look at afterwards, block ciphers, can also be used in stream cipher mode, which is fair enough for us. So I should add that they're called stream ciphers because you can encrypt a stream of data. So typically the way this extraction algorithm will work is not that it will output this entire string O at once, but it will start by outputting the first bit, the second bit, the third bit, the fourth bit, the fifth bit, the sixth bit. So this string is output like a few bits at a time. And then you get these bits, you XOR them to the message, get the ciphertext, and then you get more bits that then you can XOR with the message and get the ciphertext. So you can encrypt the first bits here before you compute the last bits here of the stream cipher. So you get this stream feeling. Okay, so the much more important tool in cryptography are block ciphers. So block ciphers are cryptographic objects which take as input a fixed length key, typically 128 bits, and a block. So they take a block which is also fixed size, can be 128 bits or something like that. The most used block cipher is probably the AES, the Advanced Encryption Standard. This was chosen in a public competition which the National Institute of Standards and Technology, NIST, ran some years ago, where cryptographers from all over the world were invited to submit their proposals for a new encryption scheme. This was a completely open and transparent process where researchers submitted the design, and then for a number of years, for 2-3 years after the submissions were sent in, all cryptographers on the planet were attacking each other's encryption schemes. And then at the end, a small set of candidates were found, which were deemed to be secure. And then Rijendel, the original name of the algorithm is Rijendel, designed by a group of Belgian cryptographers, was chosen because it was the fastest. And then it became the AES, the Advanced Encryption Standard. When you use block ciphers, you have, again, the problem of the penguin. What is the problem of the penguin? The problem is that if you take a block cipher and you encrypt messages in, and you encrypt multiple times the same block, you will get multiple times the same. If you encrypt the same block with the same key, you will get the same ciphertext. So if you encrypt the penguin using a block cipher block by block, you will encrypt this first block, this white block, and you will get this. You will encrypt the second block, white block here, and you will get this. And the output will be the same. So you will get all the structure in the plain text will be carried over to the ciphertext. And this is really bad, as you again can see from the penguin. So when you use a block cipher, it's very important to also use a mode of operation. One of the most popular modes of operation is CBC mode of operation. So what is the CBC mode of operation? The CBC mode of operation is a way of using a block cipher that doesn't suffer from the previous problem. So the problem of if you encrypt the same block twice, you get the same ciphertext. So in CBC, you take the message here and you split it into blocks. So maybe your original message was 1 megabyte long, and then you split it into blocks of equal length of 128 bits. If the final block is not, if the message is not a multiple of 128 bits, then you will just put some padding in the last block. So now you have all of these blocks. What do? So you start by choosing a nonce. In this case, it's called IV for initialization vector, which is the terminology you usually use for nonces in the context of modes of operation. So IV, initialization vector. In CBC, this has to be chosen as a random string. So you choose a random number here. You XOR this random number with the message. You get some value. Now you encrypt that using the block cipher, and you call this the first block of your ciphertext. You now repeat the process by taking this block of ciphertext, XORing it with the message, and encrypting it back and getting the ciphertext. You repeat this process until the last block, where you get the last block of the ciphertext. So now what the sender sends to the receiver are all the block of the ciphertext together with the IV. It's very important to also send the first block, the IV, it's called C0, because otherwise it would be impossible to decrypt. You can think about how you would do the decryption. So if you do the decryption, how would you do this? So when you decrypt, the receiver has all the green blocks and has to retrieve the orange blocks. So you can take C1 and you can run it the opposite way through the encryption algorithm, so you can decrypt it and you get the value which is here. Now you take this value, you XOR it with the first block C0, and you get the message 1. So this is why you need to have the IV2. So the IV is sent together with the ciphertext. So why is the CBC mode of operation secure? What happens if you encrypt the same message twice? Let's say that M1 and M2 were the same value. You have to look at what is the input of the block cipher. So if M1 and M2 were the same value, the input to AK will not be, in the first and the second case, will not be the same. Why? Because here you get M1, you XOR it with the IV, you get some value. Now you throw this through this encryption algorithm, and this encryption algorithm will output something which is going to look random or quite unrelated to IV. So C1 will be different from C0. So then when you XOR the same message with C1, which is different, you will have a different input to the encryption algorithm, and therefore you will get a different ciphertext block here. So your ciphertext blocks here will be different, and you will not be able to see the structure of the message. So even if some blocks are the same, this information will not carry over to the ciphertext. A different encryption scheme, a different mode of operation for block ciphers is counter mode. Counter mode is much more similar to these stream ciphers we've seen before, and works as follows. Also in counter mode, you have to start with an IV, an initialization vector, which is just a random number. And then what you input to the block ciphers are the IV plus 1, IV plus 2, IV plus 3, IV plus 4, and so on, where this addition is taken modulo, it's a modular addition, so it's taken modulo 2 to the 128, if that's the length of your messages, meaning that it wraps around. So all the inputs to this AK are different, because I mean, you will never encrypt as much data as the possible values of the input. So all the inputs to the AK are different, and this will produce all of these outputs O1 to ON, which are going to be just some random looking values, which you can then use to XOR one by one with the message and get your ciphertext blocks. As you can see, when you do counter mode encryption, you can start doing this, compute these O's before you know what the message is. So you can compute these, and then you can XOR with the message when the message arrives. So this looks much more like a stream cipher, like we did before. The way you would decrypt counter mode is that you would, so what does the sender send to the receiver? Again, the sender sends all of the ciphertext blocks together with the IV, the seed0. This is very important. And now the receiver will decrypt by recomputing these blocks O1 to ON. You can do that because they have the IV, and they can add 1, 2, 3, 4, blah, blah, blah. And then you can XOR these to the ciphertext blocks and retrieve the message. So this is how counter mode works. So what we covered in these last two videos was these two boxes of the taxonomy. So we looked at confidentiality. So the goal of the last two videos was, how do we protect the secrecy of the messages? How do we make sure that an adversary cannot read the messages we send? We did not talk about how to make sure that the messages are not changed on the, in transit. We want to make sure that the messages cannot be read. We looked in the first video at one-time pad, which is pretty much the only solution we have, which has unconditional security. It's secure no matter how powerful the adversary is. And then we looked, but as the big disadvantage that you can only use the keys once, and therefore it's very impractical. And then we looked at more practical encryption schemes, which have computational security and secret key. So those are stream ciphers, block ciphers. And when you use a block cipher, you have to use a mode of operation. We spend some time talking about modes of operation and why they're important. And the main reason why they're important is the penguin. Remember the penguin? If you encrypt the same message twice, you shouldn't get the same ciphertext twice. Otherwise, information about the message leaks.